And I guess I'll get started now. So
Yep.
today I'll be talking about graph C-star algebras, but I think first, before even getting into graph C-star algebras, I'll talk about universal C-star algebras, because there's some things about universal C-star algebras that I think are really useful to know here. So let's get into that. So when I say universal C-star algebra, I mean some C-star algebra which is universal for a set of generators and relations. So we'll let S be some set, which I'll call the generators. And now I have to say what we mean by a relation. So by a relation, I mean just some non-commutative polynomial in the members of S. So every relation R is going to be a non-commutative polynomial in the members of S. So for example, I could have the set S just containing a single element U, and the set R is going to be a set of relations. So that's going to be a set of polynomials in U. And since we're not assuming C-star algebras have units, these polynomials shouldn't have necessarily constant terms. So, but I could have the relation U star U minus U. So in a C-star algebra, this would be 0 if U is a partial isometry. And I could have the relation U star U minus U star. And what we're going to do is look at C-star algebras which contain elements U which satisfy that both of these polynomials are 0. So we'll call the set S with its set of relations, the pair is going to be a set of generators and relations. For our C-star algebra, which we haven't yet constructed. But if we have a pair of generators and relations, we can think about representing them in a C-star algebra. So a C-star representation of a pair of generators and relations is some function, call it J, from S into a C-star algebra A. Such that when you evaluate the polynomials in the set of relations R at the elements J of S, so I'm using just R of J for that notation. Whenever you evaluate that polynomial in R at that set of elements in A, you get 0. So here, R of j again just means evaluate R at the elements j of s, which correspond to the inputs. So then R of j is a member of A, and to have a C-star representation, we want each one of those polynomials evaluated at these elements to give you 0 in the C-star algebra. So with our previous set of generators and relations, I can show you what a C-star representation of those generators and relations looks like. So we'll define J, which goes from S, which is just the single element set containing U, into continuous functions on the unit circle. And it sends U to the identity function, which I'll call Z. Then J is a C-star representation of these generators and relations. And to check that, I would evaluate both of these polynomials at U. So for the first polynomial, I have to check that Z bar, Z minus Z is equal to 0. And for the second one, I have to check that Z bar minus Z bar Z is equal to 0, which of course they're both true. So that's what makes it a C-star representation. And I did forget to mention that these polynomials aren't just polynomials in the set S, but they're polynomials in the set of elements of S and their adjoints. But you can see that in this example. I'm taking polynomials in U and U star. And these are non-commutative polynomials, of course, because our C-star algebras don't have to be commutative, even though in this case, continuous functions on the circle is commutative. Anyways, we get a C-star representation for our previous example. Okay, so suppose we have a set of generators and relations. And some C-star representation. Then we'll call this C-star representation universal if it satisfies a certain universal property. So I'll call the pair J with A. So this pair is universal if for every other C-star representation, say iota, of my generators and relations into some C-star algebra B, there exists some unique star homomorphism call it pi from A into B, such that j pi composed with j is equal to iota. Or in other words, you have a commutative diagram where, see, at the top we have j, the left we have iota, and then pi is a unique star homomorphism that exists going from A to B, which makes this diagram commute. And because of this universal property, universal C-star representations are unique up to isomorphism. So you just apply the universal property twice. So we'll name the universal C, and then A is called the universal C-star algebra, which is unique up to isomorphism because of the universal property. So we'll call that C-star algebra C-star of S and R. If it exists. But the thing to realize is that it does not have to exist for every possible set of generators and relations you come up with. So in our previous example, we have C-star of S with R. So S is a set just containing U, and R is those relations. This universal C-star algebra is actually isomorphic to continuous functions on the circle, and that representation I gave is universal. So you can see that because the first relation here tells you that in any C-star representation, U has to be a partial isometry. And the second relation tells you that the source and range projections have to be the same. And combined with the first relation, you also get that the source and range projections are an identity for the algebra of polynomials in U and U star. So then the C-star algebra, which is universal for these generators and relations, is the C-star algebra, which is universal for a unitary, which I think you guys have seen that that's continuous functions on the circle. But again, this universal C-star algebra doesn't have to exist. For example, if I just had a single element, say S, in S, and I had no relations, then there would be no universal C-star algebra. The problem is that there's no natural way of assigning that element a norm. But here's the theorem that resolves this. Say we have some generators and relations. Then C-star of S with R exists, the universal C-star algebra, if and only if for all, say, X in S, the set I'm about to write down is bounded. It's the set of norms of j of x, where j is a C-star representation of the pair SR. So in our previous example, the universal C-star algebra exists because, well, first let's say if U, the set containing U, is equal to S, and U star U minus U is some relation, then C star of S with R exists, universal C-star algebra. Since in that case, if you have a C-star representation, J of U is a partial isometry, by this relation, we get J of U star J of U is equal to J of U. And any partial isometry has non at most 1. So this set I defined in the theorem is bounded by 1. So this is the criteria for when universal C-star algebras for some set of generators and relations actually exists. One thing to note is that by the universal property, it's actually easy to construct representations of the universal C-star algebra. All you have to do is find any C-star representation for that set of generators and relations. And if you don't care about the range of your representation, then you can choose any operators you like as long as they satisfy the relations. But it's really hard to prove that such a representation is faithful. For a general set of generators and relations, you can construct a representation, but actually proving that it's universal, or in other words, that, or not, I guess not technically in other words, but actually proving that that representation is faithful is really difficult, because you essentially, the only tool you have to prove that it's faithful is to show that the image satisfies the universal property as well. And then you have to prove something about every possible C-star representation for the generators and relations. Okay, so that's what I have to say about universal C-star algebras. And now let's specialize to graph algebras. So these are algebras that you construct from some directed graph. For now on, I'll call them just graphs. So often, people will call graphs Graphs will describe combinatorial objects where the edges don't have a direction, but here they do. So a graph is going to be a collection of vertices, which I'll label E0, edges, which I'll label as E1, R, and S, which are functions. We'll call those four things E for the graph E. So again, E0 is the vertices, E1 is the edges, R and S are functions from E1 into E0. Think of R and S as functions which tell you which direction an edge points. So for example, if I could draw a graph with just maybe two edges, two vertices, or I guess three edges if I'm drawing it this way. Yeah. So I could call this edge E, this edge F, and this edge G, this vertex V, this vertex W. So E0 is the set containing V and W. E1 is the set containing E, F, and G. And then, for example, the range of E, that's the vertex E points into, which is the same as the vertex E comes from. So that's the source of E. Both of those are W. Range of G is W, and source of G is V. And you can think about paths in a graph just by composing edges together. And then it's easy to remember which set is the vertices and which set is the edges, because the exponent is just the length of the path. So vertices are paths length 0, edges are paths length 1. So every directed graph has a universal C-star algebra. It's universal for the set of generators and relations I'll describe now. And we'll call it C-star D. So the generators are T sub E, where E is any edge, and T sub V, where V is any vertex. And the relations are given by these four rules. First, T sub E star T sub E is T sub S sub E for, say, an edge E. Second, T sub E, T sub S sub E is T sub E, again for an edge. Also, T sub range of E, T sub E is T sub E, again for an edge, E. And now we have a relation for vertices. So the relation is that the sum over all edges whose range is V of T sub E star is T sub V. But we only have this relation if there's at least some edge which points into E. So so I can take the preimage of the range function at v, and that's the set of edges which point into v. And there has to be at least some edge which points into v. But we also want the sum to be finite when we impose this relation, because it's not exactly clear what you would mean by an infinite sum in this context. So we require also that the set of edges which point into v is finite. Now this relation is for the vertices. So you add this relation in for each vertex that satisfies this condition. Now, these relations tell you about the C-star representations. So in any C-star representation, we actually have that T sub E is a partial isometry. So if you combine relations 1 and 2, you get TE, TE star, TE is TE. And then relation 1 tells you that each T sub S sub E is a projection. And now I'm realizing that if you have a vertex which isn't the source of any edge, then these relations don't tell you that the vertex is a projection, but that's something you require. So I think my notes that I'm using don't have that relation, but I need that. So quickly, just going to add this extra condition. Each T sub V does need to be a projection. So it's my mistake. But if you didn't have this relation and say every vertex was the source of some edge, then relation 1 would tell you that T sub V is a projection because it's the source projection for the partial isometry TE. And that was the point I wanted to make. T sub the source of E is the source projection for T sub E. Moreover, relation 3 implies that the range projection for partial isometry is contained in the range projection, in the projection T sub range of E. And for example, we could consider just a graph with a single vertex and a single edge, say E and V, then C star V is universal for a single unitary T sub E. So the C star algebra for this graph is isomorphic to continuous functions on the unit circle. Here's another useful example, you could take a graph with n vertices all connected in a line with edges. Then C star of E is isomorphic to the n by n matrices. But you could do this with countably many vertices. And you get that the C star algebra of that graph is isomorphic to the compact operators on some separable Hilbert space. So, like I mentioned, for general generators and relations, it's very difficult to construct faithful representations of the C star algebra. But for graphs, for example, I know that C star algebra. I know these C star algebras, and in general, for graph C star algebras, it's pretty easy comparatively to construct injective or faithful representations of your C star algebra, of the graph C star algebra. And that's the nice thing about graph C star algebras. So it stems from the theorem now that I have to describe, which uses the following action. So we have an action of the unit circle so that is some gamma, gamma which assigns to each unit, each complex number norm 1, an automorphism of the graph C star algebra. And you can see this using the generators and relations. So I should say, I guess, in the relations that I have above, which I will scroll back to, replace some edge, some t sub e for some edge, with, say, z times t sub e, where z has norm 1. And replace t sub e with just t sub e. So don't change the t sub e's. If you do that with relation 1, the z and z bar in relation 1 will cancel. See, relation 1 is still satisfied. Likewise, relation 2 is still satisfied. Relation 3. Relation 4, again, the z and z bar will cancel. And then relation 5 doesn't matter since we're not changing the t sub e's. anyways, you define this function, if you will, which send j from the generators into C star of E, which sends T sub E to Z T sub E and T sub V to T sub V. Then J itself is a C star representation of the graph C star algebra. So there's some homomorphism gamma sub Z from C star of E to C star of E. And it satisfies gamma of Z applied to T sub E is Z T sub E. Gamma of Z of a vertex projection is the same vertex projection. And that's just from the universal property. And gamma of Z is actually an automorphism. You can see that because gamma of Z composed with gamma of W, gamma sub W, is gamma of ZW. So gamma Z composed with gamma Z bar is the identity. And then this gamma of Z, that's the automorphism you get for this action of the unit circle. So this is called the gauge action. And the gauge action gives us a tool for checking whether a representation of the graph C star algebra is faithful, called the gauge invariant uniqueness theorem. Okay, so suppose we have a star homomorphism from a graph C star algebra into a C star algebra A, and say capital gamma is some action on A, which is equivariant with respect to the gauge action. So by that I mean gamma sub Z composed with pi is equal to pi composed with gamma Z. Then you have pi is injective if and only if pi of each vertex projection is not 0. So this gives you a way of checking whether representations of the graph C star algebra are faithful, and it's a very, I think in general, this is atypical of universal C star algebras to have such a, much easier condition to check whether star homomorphisms are injective like this. And maybe one thing to understand is that ideals in a universal C-star algebra don't even have to contain any elements which are finite sums of words in the generators and their adjoints. In other words, you can have ideals in universal C-star algebras which don't even contain the algebra of generators. And here I mean algebra, not the closure of the algebra, which would be the universal C-star algebra. So another way of rephrasing this theorem is that every gauge invariant ideal contains a vertex projection, or so I guess I should say every non-zero gauge invariant ideal actually not only contains an element of which is in the algebra of generators, but it contains even a vertex projection. And here gauge invariant means the gauge action sends the ideal into itself. And anytime you have a gauge invariant ideal, you take the quotient homomorphism and you get a gauge equivariant star homomorphism and vice versa. So this is surprising from the perspective of universal C-star algebras. But you can do even better for most graphs. So you also have the Kunz-Krieger uniqueness theorem. It says that if you have some graph where every cycle has an entry, so this is called condition L. E satisfies condition L. Then a star homomorphism pi is injective if and only if the image of each vertex projection is not zero. So you don't even have to check whether a star homomorphism is gauge equivariant. In other words, every non-zero ideal in the graph C-star algebra contains one of these vertex projections. Again, very unexpected for just a universal C-star, a general universal C-star algebra. And actually, so notice, Kunz-Krieger uniqueness and gauge invariant uniqueness theorem are really statements about the ideals. In gauge invariant uniqueness theorem is a statement about gauge invariant ideals, and Kunz-Krieger uniqueness is a statement about arbitrary ideals in a graph C-star algebra which satisfies condition L. You can say a lot more about the gauge invariant ideals. I guess before I get into that, I should give some examples. So for example, you could have a single vertex, a single edge. Then this loop here is a cycle, but it has no entry, so there's no other edge going into that cycle. So it doesn't satisfy condition L. So I can't apply Kuntz-Krieger uniqueness. And I know I can't apply Kuntz-Krieger uniqueness because I can come up with a non-zero ideal which doesn't contain the vertex projection. So here, say pi from C star of E into continuous functions on the circle will represent the C-star algebra of this into continuous functions on the circle. We'll say pi is the following isomorphism. Sending T sub E to the identity, which I'll call just a T, and T sub V to the constant function 1, which is the unit in the continuous functions on the circle. So we can say we have this isomorphism here. So now I can think about ideals in the continuous functions on the circle. Every ideal in the algebra of continuous functions on some locally compact Hausdorff space is just corresponds with a closed subset of that space. So I can think about closed subsets of the unit circle. And we'll say C is the set of complex numbers so that the imaginary part of Z is less than or equal to 0. So then the set of continuous functions for which are supported on the complement of C. So in other words, the image of this closed set is 0. This is an ideal in continuous functions on the circle. And this is an ideal which does not contain the unit. The only vertex projection. So pi of TV is not contained in this ideal. If it was, then that would be the unit contained in the ideal. So the ideal would contain every continuous function on the unit circle, but clearly that's not the case. And therefore pi inverse of the ideal is an ideal which is non-zero and doesn't contain the only vertex projection. So Kunstler uniqueness fails spectacularly. But also notice that we don't have you can also see that we don't have that pi is gauge equivariant. So mainly I'm referring to this gauge invariant uniqueness theorem. This condition here actually tells you what the action on the image would have to be. So if we had gamma z composed with pi is equal to pi composed with lowercase gamma, so the gauge action, then gamma z evaluated at the, oh, now this conflicts with, so let me use gamma w, since it conflicts with my notation for the identity function. Okay, so then gamma w evaluated at the identity function, that's gamma w composed with pi evaluated at t sub e, which, if this were true, would equal pi composed with the gauge action at t sub e, which would be pi of w t sub e. That's what the gauge action does. Which would equal w pi of t sub e, since pi is a star homomorphism. So that would be w times the identity. So if we had this action gamma, if we had this action gamma on continuous functions of the circle, which was gauge equivariant, then this is what it would have to be. It would have to send the identity function to w times the identity function. Now so you can see that pi actually is injective because we do have this action of the continuous functions on the circle. See, if you take the identity function, you multiply it by w, and you send the unit to the unit, then you're really rotating the unit circle. So this is an automorphism of continuous functions on a circle. This multiplication by multiplying the identity by w. It rotates by w. Okay, but I made this comment that the gauge invariant uniqueness theorem is the same as saying that every gauge invariant ideal contains a vertex projection. Now we have this ideal which does not contain a vertex projection, so there can't be a gauge action on here, which is equivariant. So because of this calculation here, it would still have to be rotation by w. But notice we're taking all the continuous functions which are supported on the complement of this closed set. And if we rotate the complement of the closed set around the circle, it's no longer contained in the complement of the closed set. So you can see that this ideal isn't gauge invariant. Or I guess I should say pi inverse of this ideal is not gauge invariant. And also, to my other comment about universal C ideals of universal C-star algebras not even having to contain any element of the algebra of the generators. This ideal doesn't contain any element which is, say, a polynomial in z, z star, and 1, because such a polynomial would only have finitely many roots, and this closed set is infinite. So already you can also see why that's true in this example. So contrast that with, well, just the graph where we have two edges now and a single vertex. Call the edges E and F and the vertex V. It satisfies condition L. Because a cycle here is just either the edge E, this loop, or the edge F, this loop. And each one of them contains an entry. The entry is the other edge, not in the cycle. You could say, well, E, F is a cycle, but by cycle I mean some path which only passes through V at the beginning and at the end, and not in the middle. So here, what I mean by cycle, the only cycles are E and F themselves, and the entry is the other edge. So it satisfies condition L. So every ideal contains the vertex prediction TV, but for this C-star algebra, TV is an identity, so every ideal contains the identity. Every non-zero ideal contains the identity. Therefore, C-star V by the Kunz-Krieger uniqueness is simple. And what is C-star V? It's this algebra O2 called the Kunz algebra.
Yeah.
Yep. And this is the C-star algebra, which is universal for two isometries which sum to the identity. Or I guess whose ranges sum to the identity. So these are range projections, and when you add them together, you get the identity. And I said something about, classification of gauge invariant ideals, but it turns out I didn't have time, so that's completely fine, because I can stop here. So I'm gonna stop the recording.